Imagine a fighter so secret that its real radar signature stays classified today, and the pilot who tested it once flew for the losing side. Built to dominate the skies and crush enemy fighters, yet in real combat, this legend has only ever dropped bombs, never killed another jet. The Pentagon planned 750 of them at $40 million each, but something crushed those numbers and pushed prices into territory Congress couldn't ignore. Its rival was faster, more elegant, arguably even superior in flight, yet you've probably never heard of it, and there's a chilling reason why. Stay with me till the end, because behind this jet hide scandals, brutal cuts, a permanent export ban, and one decision that reshaped aviation forever. Fifth-generation fighters dominate every aviation discussion you'll find online today. Yet ask anyone what the term actually means, and you'll get a different answer. Only a handful of nations on Earth can build such aircraft, and thousands of people argue endlessly about which jet truly belongs to this elite club. Here's a strange truth nobody mentions. There isn't a single official document anywhere in the world that defines clear criteria for fifth-generation fighters. The benchmark we all use today comes from one specific American aircraft, designed in the 90s, whose unique abilities effectively created the standard for everything that followed. This machine had qualities no fourth-generation fighter possessed, and from that very gap, the entire concept of the next generation was born and shaped. Its history spans 3 full decades, a fight for survival against a powerful rival, years of testing, military service, and a controversial production hold. Today, its fleet is being modernized to extend service life and boost combat potential. But how did this legendary aircraft come to exist in the first place? You're watching the story of the Lockheed Martin F-22 Raptor. The jet that didn't just join a generation, it defined one. When the F-22 first took to the skies on September 7, 1997, it shook the entire aviation world to its core. By that moment, Lockheed Martin had already announced flight characteristics and technical specs, yet the company didn't actually have real data on its own aircraft. 8 prototype jets still had to complete a testing program lasting 5,000 flight hours before anyone could verify the bold claims being made publicly. But these numbers weren't pulled from thin air. They came from an earlier competition called ATF, designed to find the next air superiority fighter. Lockheed Martin entered with the YF-22 demonstrator and emerged as the winner, and the future F-22 would be built on that prototype's proven foundation. The Raptor inherited every defining trait of fourth-generation fighters, but added a set of completely new capabilities that expanded combat potential dramatically. First came radical reduction in radar and infrared signatures. The airframe used radar-deflecting shapes and absorbing materials, while flat nozzles cooled exhaust gases to hide heat. Next came supersonic cruise without afterburners, a tactical advantage that combined with stealth could change the entire shape of an air engagement. Engines received thrust vectoring nozzles that dramatically improved control at low speeds and extreme angles of attack. A true revolution in fighter maneuverability. All these qualities were tied together by an electronics suite, featuring an active phased array radar and a passive 360-degree threat warning station. To understand why the F-22 turned out exactly this way, you need to dig into history, back to 1976, and a different remarkable fighter. That year, the U.S. Air Force received the McDonnell Douglas F-15, a fourth-generation jet built to replace the aging F-4 Phantom II. The F-15 outclassed its predecessor in maneuverability, applying lessons from clashes with Soviet MiG-21s, and offered a far more advanced radar with new missile options. With F-15C and twin-seat F-15D variants, this jet became the backbone of American air superiority. Yet planners already started thinking about its replacement. Here's the punchline you didn't expect. The F-15 was savagely criticized for costing 5 to 7 times more than late-model F-4 Phantoms. That cost crisis directly led to the cheaper, lighter General Dynamics F-16, and, ironically, this exact pattern would later repeat itself with the F-22. To shape the next-generation air superiority fighter, the Air Force launched a research program called ATF, Advanced Tactical Fighter, whose details remain partly classified today. In 1983, the requirements were sent to leading American aircraft and engine manufacturers to determine whether such an ambitious concept was even physically achievable. The future fighter had to deliver three core capabilities: reduced signatures, supersonic cruise without afterburners, and short takeoff and landing distances. Stealth had never before been a primary requirement for any fighter, and the reason it appeared now traces back to one specific aircraft that changed everything. The Lockheed F-117 Nighthawk, born in the early 80s, was the first piloted combat aircraft built entirely around the principle of being unseen. Its faceted shape deflected radar signals, weapons hid in an internal bay, joints had sawtooth edges, and flat nozzles masked thermal signature with cool airflow. The results stunned the military. Detection range collapsed dramatically, and the Air Force decided this same magic had to be transferred onto a maneuverable fighter. But here's where it got brutally difficult. Every stealth measure damaged aerodynamics, and the moment you sacrifice aerodynamics, maneuverability suffers right along with it. The second pillar was supersonic cruise without afterburner, saving fuel, extending range at high speeds, and dramatically reducing thermal visibility to enemy infrared sensors. Until then, only two aircraft in history had managed this: the Anglo-French Concorde and the Soviet Tu-144D, both passenger jets, and neither built for combat. By the mid-80s, the final ATF requirements were locked in, and the customer demanded a machine vastly superior to anything F-15C could ever achieve. In autumn 1986, the main contractors were chosen, given 4 years to build prototypes and prove their concepts in head-to-head flight comparisons. The climax came in late 1990, and what unfolded on those test flights would determine the future shape of air combat for the next half-century. Lockheed teamed up with Boeing and General Dynamics, fielding 2 prototypes designated YF-22, while Northrop joined McDonnell Douglas to bring forward 2 YF-23 demonstrators. Engine makers competed too. Pratt & Whitney offered the YF-119, General Electric the YF-120, and both engines had to be tested in both airframes. The Northrop YF-23 was the showstopper. Diamond-shaped wing of huge area, no conventional tail, just 2 angled, all-moving surfaces, giving it an alien silhouette. The Lockheed YF-22 looked far more conservative by comparison, its layout closer to the familiar F-15, a design choice that puzzled many observers at the time. Flight testing of all 4 prototypes ran from August through December 1990, and in April 1991, the Air Force finally announced the long-awaited winner. The Lockheed YF-22, with the Pratt & Whitney YF-119 engine, was selected for full-scale development. But officials never publicly explained the reasoning behind this choice. Both rivals had met all the core ATF conditions, demonstrating low signatures, supersonic cruise, and short takeoff distances at very similar measured levels. Yet Lockheed had flown its program much more intensively, 74 flights against Northrop's 50, and the details inside that data hid the real answer. The Air Force had picked long-range missile combat as the primary tactic, where stealthy fighters fire first from huge distances without entering visual range. Their main weapon would be the new AIM-120 AMRAAM, capable of striking targets up to 70 kilometers away. Both prototypes handled this scenario competently. But things looked entirely different at low subsonic speeds. And here, Lockheed's prototype had a decisive advantage, thanks to its thrust vectoring nozzles.
The YF-22 confidently maneuvered at angles of attack approaching 60 degrees, while the YF-23 maxed out near 25, far below what its designers had hoped. The Air Force concluded that in close-range combat, where engagements develop in seconds, Lockheed's design simply gave pilots a much better chance of survival. For close encounters, the future fighter would carry only 2 short-range AIM-9 sidewinders and a 20mm cannon. Every advantage in agility mattered enormously. Lockheed and its partners had also delivered more refined, less troubled prototypes, while the YF-23 still needed serious refinement to match its rival in key areas. Intake problems and oversized engine nacelles capped the YF-23's top speed at Mach 1.85, while the YF-22 in one flight pushed past Mach 2. Internal weapons bay testing on the YF-23 was limited to acoustic checks, while the YF-22 actually fired both missile types from its bays in flight. Despite the technical struggles and final loss, Northrop and McDonnell Douglas built something genuinely beautiful. Many still consider the YF-23 the more elegant overall design. Its all-moving twin-tail surfaces and upper-mounted nozzles, borrowed from the B-2 Spirit bomber, even contributed to lift through the Coanda effect, called supercirculation. Even with its flaws, the YF-23 actually outperformed the YF-22 in supersonic cruise speed, range, and takeoff distance. A haunting what-if for aviation enthusiasts. Both Northrop prototypes never flew again and were eventually transferred to museums, where they remain beautiful ghosts of an alternate future for American air power. Lockheed continued research flights with one of its YF-22s until April 1992, when an accident during a simulated landing approach finally grounded the test program. The damaged jet was later restored and displayed at the 50th anniversary celebration of the U.S. Air Force, a fitting tribute to a pioneering machine. The new air superiority fighter received the official designation Lockheed Martin F-22A, with the corporate name change reflecting the 1996 merger with Martin Marietta. In that same year, the F-22 received its proper name, Raptor, though earlier it had been informally called Lightning II, after the legendary World War II P-38. That nickname, Lightning II, didn't stay long. Within a decade, it would be passed on to a completely different aircraft, the F-35. The original ATF program planned to buy 750 of these advanced fighters, but the future would deliver shocking corrections to that ambitious initial number. In total, only 197 flight-capable F-22s were ever built. 2 prototypes, 8 pre-production aircraft, and just 187 serial F-22A production fighters. Given such drastic cuts, you might wonder whether the F-22 ever truly replaced the F-15 in operational service. And the answer surprises most aviation watchers. Production of F-15C and its twin-seat trainer ended back in 1985, capped at 235 aircraft, meaning the youngest unit is now decades old. By Air Force plans, these jets will leave service before 2025, while the F-22 quietly began outnumbering combat-ready Eagles in active service back in the early 2010s. Here's the irony. Designed as an air superiority hunter, the F-22 has so far seen real combat only as a tactical bomber, dropping precision-guided weapons. In genuine air-to-air combat, no Raptor pilot has yet faced an enemy fighter. The legendary jet still waits for its moment of true testing. The F-22's flight career began 6 years after the ATF winner was announced,
with the first pre-production jet rolled out on April 7, 1997. Engineers promised first flight within 2 or 3 weeks, but technical problems pushed it back 4 months, until that historic September takeoff at Dobbins Air Base. Chief Test Pilot Paul Metz later said the aircraft behaved exactly like the simulator predicted, and for years afterward, Metz remained nearly the only public source. Lockheed Martin officially released only fragments of data about the jet, much of it in vague, class-based form rather than precise technical numbers. The F-22 remains one of the most secret American military projects, so most known data has been derived empirically using comparable aircraft of the same class. Here's a remarkable detail in Paul Metz's career. Before becoming chief F-22 pilot, he had flown for the rival camp during the ATF competition. Metz was on the Northrop test team and personally piloted the YF-23's very first flight, then crossed over to fly its winning competitor. When asked once to compare the two aircraft, he simply answered that comparing a prototype to a near-production fighter has no real meaning.
Designing the F-22 meant balancing impossible contradictions. Stealth, supersonic cruise, and maneuverability all pulled the design in different directions, demanding clever engineering compromises. Stealth measures had the biggest visible impact on layout. Every plane and edge of the airframe was oriented to deflect radar in strictly limited directions. Look at the F-22 from the front, and you'll see the nose, intakes, and tail fins all running parallel. A clear, stealth-driven design choice. From above, the wings, intakes, and stabilizers share parallel edges, while sawtooth seams cover hatches and panels across the entire fuselage of the aircraft. Special radar-absorbing materials are built into the structure, while scattering coatings are applied through specialized equipment to most exterior surfaces of the fighter. The intake plays a critical role in frontal stealth, because on older fighters it's the spinning compressor blades that create the biggest radar signature. The Raptor's S-shaped intake ducts physically block direct radar view of the first compressor stages, and absorbing coatings inside reduce reflections by orders of magnitude. To shield turbine blades on the exhaust side, radar blockers, radial absorbing structures, sit just behind them, soaking up reflected waves before they escape. The flat nozzles, unusual in modern aviation, give the Raptor critical qualities. Their flat exhaust plume cools faster, dramatically reducing infrared signature without afterburner use. There's a concept called radar cross-section, or RCS, which measures how visible an object is to radar in square meters under specific conditions. Under ATF rules, the new fighter's RCS had to drop at least tenfold compared to F-15, with frontal RCS reduced by even more. Real F-22 RCS values are among the most closely guarded secrets, but skeptical estimates put the average RCS between 0.1 and 0.3 square meters. Frontal RCS is likely an order of magnitude lower, and the most optimistic claims describe values comparable to a tiny steel ball, practically invisible to radar. Whether you're a skeptic or an optimist, one fact is clear. Lockheed engineers achieved a radical reduction in detectability, the foundation of survivability in modern combat. Alongside stealth, supersonic cruise without afterburner is the Raptor's other defining advantage, covering vast distances with low heat signature and reduced fuel burn. This figure for the F-22 is roughly Mach 1.5 at altitudes near 15,000 meters, about 1,600 kilometers per hour in calm atmosphere. Paul Metz mentioned in one interview that under certain conditions, the Raptor can sustain Mach 1.72 without lighting its afterburners. Staggering performance for any fighter. To achieve this, the wing uses flat profiles, low aspect ratio, and significant sweep,
geometry optimized specifically for supersonic aerodynamic efficiency at high altitudes. The Pratt & Whitney F119 engines have low bypass ratio of just 0.2. 5 times more air goes through the inner core than the outer. Exact F119 thrust figures stay secret. Manufacturer says afterburning class is around 16 tons, while military thrust is rumored at 10 to 10.5 tons. This low bypass paired with oversized intakes is the compromise that makes supersonic cruise possible, especially at high altitudes, where thin air rewards this configuration. At lower altitudes, excess airflow is dumped through bleed doors on top of the airframe, the price you pay for high-altitude dominance. ATF demanded stealth and speed first, but maneuverability requirements weren't forgotten. The new fighter had to meaningfully exceed the F-15 in agility and turn rate. Even during YF-22 tests, it became clear that Lockheed's concept worked. The prototypes had excellent acceleration and handled high angles of attack confidently. The production F-22 differed significantly from the prototype. Wingspan grew, sweep decreased, vertical tails shrank, and the nose was substantially reshaped for better performance. These changes reflected an effort to make the Raptor even more agile at subsonic speeds, where Su-27s and MiG-29s held an aerodynamic edge in close combat. The F-22's high agility comes from several factors: high thrust-to-weight ratio, low wing loading, high allowable G-loads, and the famous thrust-vectoring nozzle system. With full fuel and weapons, thrust-to-weight already exceeds 1, and as fuel burns down approaching the combat zone, this critical ratio rises even higher. Thrust-vectoring nozzles deflect symmetrically in pitch up to 20 degrees, working constantly together with the horizontal stabilizers to enhance overall control authority across the envelope. You'll see this at every Raptor demo. Bell maneuvers, Pugachev's Cobra, Frolov's Chakra, all pulled off by line pilots, not just specialized test crews. The Raptor's display program prefers sweeping, high-speed afterburner flying over slow, extreme-angle stunts because realistic combat rewards turn rate, not deliberate loss of energy. According to Paul Metz, vectoring nozzles also assist supersonic maneuvering. Deflecting stabilizers at high speeds creates drag that bleeds energy quickly off the airframe. The F-22's primary weapon is air-to-air missiles, all carried in 3 internal bays designed around the demands of stealth above all else in combat configuration. The large central bay houses up to 6 AIM-120 AMRAAM medium-range missiles, radar-guided weapons that can hit maneuvering targets up to 50 kilometers away. For close-in fights, 2 AIM-9 sidewinders with infrared seekers ride in the side bays, 1 each, a minimal but capable backup arsenal. If all missiles are gone, a 6-barrel 20mm Vulcan cannon with 480 rounds becomes the last line in the battle for survival in combat. Launching missiles at supersonic speeds was one of the program's hardest challenges, because opening bay doors creates powerful low-frequency vibrations that can shatter weapons or structure. Lockheed solved this using lessons from the experimental YF-12 interceptor of the 60s, whose bay doors had opened at over Mach 3 in flight tests. The tactical picture comes from the AN/APG-77 radar, paired with the AN/ALR-94 threat warning station, a combination operating with minimal radio emissions. The ALR-94 stays fully passive, scanning surroundings using over 30 receiving antennas spread across the airframe to map threats without revealing the Raptor's own position. Multiple Raptors share data through a special data link, letting pilots build a complete tactical picture, while only some jets actively radiate radar energy in the sky. This enables a brilliant tactic. Part of a flight emits and searches, while the rest stay silent and stealthy, multiplying the formation's combat effectiveness. May 2, 2012 marked a milestone for the entire program. Lockheed Martin delivered the final Raptor with serial number 4195 to the Air Force. 195 fighters built, far below original ambitions, falling short of the corporation's and Air Force's expectations from the program's optimistic beginning years earlier. In 1991, the plan called for 750 fighters at no more than $40 million each, only $10 million more than an F-15C. By 1997, the number was halved to 339 jets, and by 2004, it was finally cut to 183, with a small later adjustment to 187. Several factors triggered this collapse. In 1991, the main geopolitical rival dissolved, fueling congressional opposition and arguments that fewer fighters would suffice for emerging threats. To save the program, the Air Force expanded the F-22 mission, adding precision strike with 450-kilogram JDAMs and later 110-kilogram GBU-39 small-diameter bombs. Expanded missions couldn't save it. In 1996, the Joint Strike Fighter program launched, leading to the F-35 with maximum strike capability and lower cost. As order numbers shrank, unit cost climbed steadily, eventually forcing the early production halt. Average unit price ended near $143 million per aircraft.
That's 3 to 4 times the original target. And the same pattern played out earlier with the F-15, which became multiple times costlier than the F-4. F-22 also faced costly redesigns mid-production. Composite structural elements were replaced with titanium and aluminum after live-fire testing exposed weakness against cannon hits. In autumn 2006, the U.S. Congress imposed a permanent ban on F-22 exports. The Raptor would forever stay in American service only, never sold abroad. Today, about half the production fleet is combat-ready, with the rest progressing through a modernization program that keeps the airframe relevant for years to come. Key updates include expanded APG-77 radar functionality and integration of newer weapons, AIM-9X and AIM-120D missiles, with greater launch range than predecessors. Active Raptors regularly join exercises and generally validate their original design ideas. Flights up to 20 kilometers altitude with cruising supersonic remain unmatched in practice. F-22 has flown training engagements against French Rafale, European Typhoon, and Malaysian Su-30 MKM fighters. Public results were never released, but accounts describe mixed outcomes. The F-22 Raptor remains a defining moment in world combat aviation, a serious challenge to rivals, and a clear demonstration of advanced design philosophy. For the United States, it represents enormous scientific and technological progress, a foundation for future projects reaching well beyond aviation into other strategic domains. Even today, decades after its first flight, designers around the world still measure their next-generation fighters against the standard this single aircraft created.